What people don't recognize is that first law of thermodynamics, the law of conservation of energy, is based on instantaneous gravity. In 2017, LIGO-Virgo confirmed that gravity traveled at the maximum speed of light. Since then, there have been over 100 gravitational wave observations confirming that the velocity of gravity is actually the maximum speed of light. Since it's been confirmed that the effects of gravity travel at the maximum speed of light, the law of conservation of energy must be reevaluated. The theorized explanation of this gravity wave is that a binary system of two large masses, possibly black holes, produces a small difference in perceived gravity between the perpendicular and conjunction orientations. To demonstrate, here are the calculations of an oversimplified example. Two objects, A and B, with identical masses of 1 unit, orbit about a center of mass with a radius of 1, positioned 100 units from the observation. To oversimplify, I'll declare the gravitational constant equal to 1. When the objects are perpendicular to the line of sight, the force experienced is the mass of the observer times the acceleration, which is equal to the gravitational equation of force from A to C plus the force of B to C, which are identical, the sum of which gives a total acceleration of 2 times 10 to the power of minus 4, or less if you want to take the hypotenuse. When they're in conjunction, the one mass is a radius less, whereas the other mass is a radius greater than the distance between the center of masses. Going through the math, the sum of the accelerations is slightly more than 2 times 10 to the power of minus 4. Using my simplified values, this is a tiny difference. However, if you put in more realistic values, the difference would be so impossibly small, it would take a miracle to detect it. A miracle is granted when light beams were bounced 300 times between two mirrors 4 kilometers apart. Now, before we continue, let's look at the gravitational wave, again using oversimplified values. Let's assume there's 100 light years between the event and the observer. If the velocity of gravity were equal to the maximum speed of light, it would take 100 years for the observer to see and feel the event. However, if the velocity of gravity were 1,000 times greater than the maximum speed of light, then it would take just over a month. 1,000,000 times the speed of light would take just under an hour. 1,000,000,000 times would take just over 3 seconds, and 1,000,000,000,000 times would take just over 3 milliseconds. By using a bit of imagination and interpolation, a factor of infinity would result in instantaneous gravity velocity, resulting in 0 time between the event and the perception, regardless of the observer's location. Recognizing that it takes time for light to bounce 300 times between two mirrors 4 kilometers apart, it's understandable why the raw data has an imperfect oscillations and why they're smoothed out for the public. What's confusing is that instead of co-orbiting according to Newton, the two masses spiral inward, creating an audible chirp. This would indicate a loss of energy. Current theories of this loss of energy include transfer of mass resulting in the loss of kinetic energy, transfer of kinetic energy into rotational energy, kinetic energy transferred into radiant energy, and finally, the energy loss in producing a gravitational wave. For the first three speculations, the only mass available would be the accretion disk outside the event horizon, and this mass is hardly sufficient to cause such decay. Besides, once the matter lost enough energy to slide beneath the event horizon, it could no longer transfer energy into the universe. As for producing a gravitational wave, I've just shown that a gravitational wave exists regardless of velocity. Besides, momentum, gravity, and charge are all properties of matter and do not require energy to be produced. If they did, then the mass of planets and stars would decrease as they produce a gravitational wave, and the mass of electrons and protons would diminish in producing a charge. Let's create an ideal oversimplified scenario with two identical masses at a distance d apart, both with an initial velocity of 0. Since each observes the other the same, equations calculated for one can be applied to the other, and they would travel directly towards each other. In this way, there is no mass exchange, no transfer to rotational energy, no transfer to radiant energy. These two objects will collide at their center of mass, bounce off each other, and ascend back to, hopefully, their original locations. Three of these four analyses will be simulated here. Newton's law of universal gravitation with instantaneous gravity and no time dilation, Einstein's special relativity using Lorentz time dilation with instantaneous gravity, and the LIGO-Virgo gravity wave with the velocity of gravity equal to the maximum speed of light and no time dilation. The fourth one, which is a current view of reality, I'm going to save for a different video series. As I originally stated, the law of conservation of energy is based on the application of Newton's equations on universal gravitation applied to instantaneous gravity, velocity of gravity. The scenario begins with two identical objects with 0 velocity at distance d apart. Since the opposite equations of one can be applied to the other, they will eventually meet the center after each has traveled a distance of 1/2 d. The actual potential energy at any given time will be given by the potential energy equation shown, and is based on the product of the masses divided by the distance between them. Since the masses don't change, potential energy is only based on the inverse of the square. Likewise, the change of potential energy, or work, is proportional to the difference between the inverse of the distances. These values remain the same regardless of the velocity of gravity, because what affects one affects the other equal but opposite, and they will always collide at their center of gravity. Consequently, these equations remain valid for all time from initial to bounce to final. The change of kinetic energy is based on acceleration, which is based on where the objects perceive the other. Again, since the perceived distance remains the same, but in opposite direction, the mirrored equations of one object can be applied to the other. Since they both start with 0 velocity, they are both attracted equally but opposite to each other. Their acceleration at any time will be equal but opposite, and with equal but opposite accelerations for all time, their velocities will also be equal but opposite. Since kinetic energy is based on velocity squared, the change in kinetic energy will be based on the difference between the square of the velocities. With instantaneous velocity, there is a direct correlation between the potential energy lost and the kinetic energy gained, and this is the basis of the law of conservation of energy. In reality, a direct impact of any significant mass of the object would result in a single object, especially a black hole. However, for my proof of concept, my objects will bounce with perfect transfer of momentum. The momentum of A will be transferred to B, while the momentum of B transferred to A. Since my example has identical masses, the velocity of A would be transferred to B, while the velocity of B transferred to A. And since the velocities are equal but opposite, the positive velocity of A becomes a negative, while the negative velocity of B becomes positive. The equations for the ascent of the two objects are identical but mirrored to the equations of descent. While the descent validated the law of conservation of energy, so does the ascent. The kinetic energy lost equals the potential energy gained, and the objects reach their original locations with zero velocity at the same time. The difference in time from initial to collision equals the time from collision to final. In conclusion, when the Newtonian equations are applied with instantaneous gravity, the objects are perceived to be at their actual locations. Kinetic energy is gained proportionally as potential energy is lost during the descent, and potential energy is gained proportionally as kinetic energy is lost in the ascent. Without losses due to transfer of mass, transfer of rotational energy, or transfer of radiant energy, the system will be a perpetual condition. And this is the basis of the law of conservation of energy.